Andrew Feldman walked to the center of the stage. He held a silicon wafer the size of a dinner plate. It was not a chip in the conventional sense. It was the entire WSE3 processor. The room went quiet. Across the industry, engineers spent their lives wiring thousands of tiny chips together to build power, but Feldman held the answer to that complexity in his hands. He stopped at the server rack. The lights on the chassis pulsed, waiting. He slid the massive wafer into the slot. It clicked into place with a heavy, mechanical finality. Inside the cabinet, the system hummed. It was the sound of thousands of individual processing cores waking up at once. This was the moment the old math of semiconductor design failed. For years, the market had been built on the assumption that smaller was safer, that linking small units was the only path forward. Feldman had just ignored the rulebook entirely. As he stepped back from the rack, the screen behind him flashed a list of performance metrics. The audience shifted. This was no longer a theoretical debate about architecture. It was a direct physical confrontation. The giant sat in the rack, ready to draw power, while the industry watched the gap between the established monopoly and this new singular force begin to widen. The ambition of the WSE3 rested on a single, fragile premise. Printing a processor across an entire 300mm wafer was historically dismissed as a fool's errand. In the world of semiconductor manufacturing, perfection is a statistical ghost. Silicon is prone to microscopic imperfections. A single speck of dust or a fracture in the crystal lattice can ruin a standard chip. When that chip is tiny, the loss is negligible. When that chip spans the entire surface of the wafer, a single defect destroys the entire unit. For decades, the industry operated under this iron law of yield. If a manufacturer attempted to print a wafer-scale processor, the defect rate would reach 100%. The silicon would be useless, a multi-million-dollar slab of glass and waste. Feldman knew the history of these failures. He knew that the graveyard of silicon startups was filled with those who tried to push the physical limits of the substrate and failed. To succeed, Cerebras had to defy the fundamental physics of fabrication. If they could not master the yield, the entire project would collapse into a commercial dead end. The stakes were absolute. Every wafer that left the foundry was a gamble against the microscopic chaos of the manufacturing floor. The survival of the company depended on solving the impossible, one layer of silicon at a time. Feldman pointed to the giant screen behind him, shifting the display from hardware specs to live system diagnostics. He had not solved the problem by eliminating defects. He had solved it by making them irrelevant. The proprietary software displayed a complex map of the wafer surface, lit with thousands of active pathways. He tapped the console, and a red zone appeared, a cluster of manufacturing defects that would have crippled any other processor. The system did not falter. In a fraction of a millisecond, the software rerouted the data flow. It bypassed the dead circuits, reconnected the links, and maintained peak performance without a single drop in speed. The audience leaned in. This was the technical pivot point. By weaving intelligence directly into the fabric of the hardware, Cerebras had turned a manufacturing nightmare into a programmable architecture. The software acted as a nervous system, constantly surveying the silicon and healing the path around every microscopic flaw. It was a complete reversal of industry logic. Instead of demanding perfection from the foundry, they built a machine that thrived on imperfection. The crowd watched as the system continued to process heavy data loads despite the mapped-out failures. The old rules of semiconductor design had been shattered. Feldman stood back, letting the visualization of the rerouting process prove what the industry had once called impossible. The technical proof was one thing, but the industry was waiting for a signal. That signal arrived in the form of a $20 billion partnership with OpenAI. The news hit the market like a shockwave. For years, the venture had been dismissed by analysts as a brilliant science experiment, a niche play that would never scale. The deal silenced the critics overnight. It was not merely a contract. It was a formal endorsement from the most demanding player in the AI race. The validation rippled through the financial sector. Suddenly, the dinner plate processor was no longer a curiosity trapped in a lab. It was the engine for the future of large-scale intelligence. Investors who had held back, waiting for the inevitable failure of the silicon, began to move. The narrative shifted from technical skepticism to commercial urgency. Feldman stood at the center of this transformation, no longer explaining how the technology worked, but where it would lead. The deal established a new baseline for industry expectations. If the leading pioneers of artificial intelligence were betting their infrastructure on a single piece of silicon, the established dominance of smaller, distributed clusters was no longer the only path forward. The weight of the deal forced a reckoning in every boardroom that had previously ignored the wafer. It was the moment the industry recognized a new heavyweight had entered the ring. The validation of the technology was only the beginning. Now, the war moved to the physics of data movement. In a traditional server farm, thousands of small chips must talk to each other across complex, high-cost networks. Every time data jumps from one processor to another, there is a penalty. It is a tax on time, a bottleneck of copper and fiber that slows the entire system down. Nvidia spends millions developing proprietary interconnects just to minimize this friction, but the physical distance remains. Feldman moved to the whiteboard, drawing a simple line. He compared the distributed network to a massive, sprawling city where every citizen must drive miles to communicate. Then he drew the wafer. On the silicon surface, the distance between any 2 points is measured in millimeters, not meters. Data does not wait for slow cables. It travels across the wafer at the speed of light. The architecture eliminates the external network entirely. By keeping the communication inside the substrate, the system achieves a level of synchronization that a distributed cluster can never replicate. It is not just faster. It is a fundamental change in how information is processed. The bottleneck that had defined the hardware industry for a decade was suddenly rendered obsolete by the sheer scale of the chip. The shift in architecture was no longer a technical debate. It hit the balance sheets. When the company reported a 41% gross margin, the narrative in the financial district snapped into focus. This was not a lab project anymore. It was a business machine designed to bleed a monopoly dry. Analysts who had spent years tracking the predictable growth of established hardware giants began to scramble. They saw the numbers and realized the old rules of semiconductor profitability were failing. The stock market reacted with immediate, aggressive volatility. Capital moved. Millions of dollars shifted from traditional portfolios into the new, monolithic architecture. It was the kind of movement usually reserved for the early days of the personal computer revolution, a rare moment where a singular innovation forces an entire industry to reprise its future. The 41% margin was the smoking gun. It proved that the wafer was not just faster, but cheaper to operate at scale. Every percentage point gained was a direct strike at the heart of the existing market dominance. The boardrooms of the world took note. For the first time in a decade, the ground beneath the established empire was visibly cracking. The threat was no longer potential. It was on the ledger, and it was growing. The hardware was ready, but the fortress remained sealed for over a decade. Nvidia had built more than just chips. They had built a lifestyle for developers. Thousands of engineers had spent countless hours writing code optimized specifically for the CUDA ecosystem. This was the invisible wall standing between the wafer and total market dominance. Performance metrics on paper meant nothing to a researcher who would have to rewrite months of complex models just to switch platforms. It was a classic trap of inertia. Every line of code written in the old language acted as a tether, pulling developers back to the familiar, even if that path was inherently slower. Feldman watched the adoption rates and saw the friction. The industry was not just choosing a processor. They were choosing a workflow that they had already mastered. It was a war of habits. The superior speed of the wafer was a blunt force, but the software ecosystem was a deep, tangled root system that refused to be pulled. The company could offer the fastest compute power in the world, yet the developers held the keys to the kingdom. If they did not move, the hardware would stay in the box. The war was no longer about the silicon. It was about the code. Feldman knew the hardware war was only half the battle. He gathered his lead engineers in a windowless room, the air thick with the smell of cooling fans and stale coffee. They were staring at a wall of data that showed stagnant migration rates. Developers were not moving because the cost of rewriting their models was simply too high. He drew a line through the existing complex stack on the whiteboard. The directive was absolute. Stop chasing raw speed and start chasing simplicity. If a researcher could not migrate their code in a single afternoon, the hardware was useless. The team worked in shifts, stripping away layers of complexity that had been standard for years. They built new compilers that could ingest old code and translate it into the language of the wafer. It was a brutal, granular process of refinement. Every feature added to the software layer was a direct assault on the Nvidia ecosystem. Feldman pushed them to prioritize the user experience of the developer above all else. By the end of the month, the first beta tools were ready. They were not just software. They were keys designed to unlock the fortress. The offensive had begun. Now, they waited to see if the developers would take the bait. The battlefield had shifted from code repositories to the cold hum of the world's most critical data centers. Every rack installed was a physical vote for the future of artificial intelligence. Engineers in facilities from Virginia to Singapore were sliding the massive processors into place, replacing the traditional clusters that had defined a decade of computing. The change was silent but absolute. Where once there were thousands of cables and complex interconnects, there was now a single, unified surface. The physical footprint of these data centers began to shrink as the wafer architecture took over. Every unit shipped represented a rejection of the old, fragmented status quo. Managers watched the power consumption metrics drop while compute efficiency spiked. The data was no longer just a trend on a spreadsheet. It was a tangible shift in how the world processed information. Customers were moving beyond the hesitation of the software transition, choosing the raw, concentrated power of the wafer over the distributed complexity of the past. As the racks multiplied, the signal became undeniable. The wafer was not just an experiment anymore. It had become the new foundation of the global infrastructure, one physical installation at a time. The monopoly remains, a titan entrenched in the bedrock of software and habit. But the ground beneath it has moved. The era of building massive, complex networks of small chips is no longer the only path forward. Performance has finally triumphed over the status quo. The dinner plate chip once dismissed as a laboratory curiosity, now sits at the heart of the world's most critical AI workloads. It has proven that a singular, unified vision can outperform a decade of incremental, fragmented progress. Complexity has reached its limit. The industry is watching as the wafer-scale architecture carves out its place in the history of computing. This is not the end of a conflict, but the dawn of a new standard. Developers who once hesitated now migrate their models to the silicon surface, drawn by efficiency that was previously impossible. The shift is subtle, measured in gigahertz and latency, but it is absolute. The rules of the semiconductor game have been rewritten. For the first time in 10 years, the future of artificial intelligence does not belong to the established order alone. It belongs to the architecture that dared to think bigger.